going to pose a question, which is, what are the four states of matter? And I would argue that three of those states of matter we are intimately familiar with at all times. Three of them are solids and liquids and gases. And where we live on the Earth, we're pretty much surrounded by those states of matter. Solids is represented by blocks of ice. We apply heat, increase the temperature, it melts, becomes a liquid. Apply more heat, it becomes a gas. Now, what happens if we continue to apply energy and increase the temperature of the system? The atoms in that system begin to move faster, they collide with each other much harder, and eventually they undergo a process known as ionization. And when ionization occurs, it means it lifts the outer electrons off, and you form a new state of matter, which is called a plasma. It's a type of ionized gas, and here on the Earth, it's really hard to actually make naturally occurring plasmas. They generally only occur in things like bolts of lightning or the aurora. However, outside of the Earth, plasmas are, in fact, one of the most common forms of matter. 99% of the matter in the visible universe is, in fact, in the plasma state. Because of that, plasmas are used to address some of the most fundamental issues that we can think of in science. Questions like, how do gas and plasma and dust come together to form planets? How do currents inside of stars, inside of the hot plasma inside of stars, come together to generate magnetic fields and in turn magnetize the entire universe? And then more locally, how do stars and planets become connected to each other through the outflow of plasma from stars in something called the solar wind? But these are not just theoretical questions. These are questions that have really practical benefit. For example, the same chemical and physical processes that occur inside of planets, inside of star-forming regions, are the same ones that we use and apply for using for plasma technologies and the new emerging science of plasma medicine. We use magnetic bottles, combining them with hot plasmas in a technology called fusion energy, and in our quest to actually make a star here on Earth. And we are embedded and surrounded by a fleet of satellites that are sitting inside of this environment where the solar plasma interacts with the Earth. And we want to understand that space weather. And the beauty is that Auburn's physics department is actually engaged in research in all of these different areas. Now, in my laboratory, we focus on a particular type of plasma known as a complex or a dusty plasma. And I'm going to use those terms interchangeably. And what exactly do we mean by a dusty plasma? So what I'm going to do is I'm going to make a plasma in a laboratory right here. I'm going to, it's this hot, this kind of glowing, gassy thing. I'm going to have a collection of glass beads. These beads are pretty small. They're typically about the size of your hair. So to put them to scale, we shrink them down, we shake them inside the experiment, and then we turn on a laser, and then we look at a particular part of the experiment, and when we do that, what we get is something quite remarkable. All right, we'll keep the audio going. These are examples of small particles that are actually flowing in the plasma and are actually circulating and doing all sorts of really remarkable things. Now, one of the really key features of complex plasmas is that by adjusting the temperature and the conditions in the experiment, we can actually make a transition of the dust component, the particle component of the plasma, to actually begin to behave solid-like, or liquid-like, or gas-like, all by just simply controlling the conditions in the experiment. And the beauty of this is that means now where you normally can't see the individual atoms in solids or liquids or gases, you can see the particles in this system and actually be able to study the physics of all of these types of systems while inside of a plasma environment. So I want to talk about two different experiments that my group is involved in. Both are very active collaborations with our community. The first of these is going to be talking about fluid-like experiments on the International Space Station. So the question is, why do we want to lift the experiment and carry it into space? Well, the little particles are very heavy compared to the ions and the electrons and the neutral atoms that are inside the system. As a result, when we do experiments on the ground with gravity, the whole system tends to get compressed and what's called undergo sedimentation. If you remove gravity, then the system expands and becomes large and three-dimensional and allows us to now study a lot of the dynamics of the system that you can't do on Earth. And so that's what we do. There's been a series of experiments done by our German and Russian collaborators that have done experiments on the space station for many years. This is the most recent of them, this U-shaped tube that has particles that are going to flow inside of it. There's a cosmonaut actually taking the instrument on board the space station. And then you get this remarkable system with these flows and waves and things like that that are actually quite challenging to produce on Earth. Our contribution to this type of research is actually in the form of flow analysis. Here's the experimental data. There are velocity vectors, basically measurements of how fast the particles are flowing inside of this system. And we use our particular expertise, our particular technical capabilities of being able to measure flows and also to look at the thermodynamic properties of these systems. And that's one of the things that we can do and we can contribute to these space station experiments. Now, the other type of experiment we're actually doing here in Auburn, which is actually to study complex plasmas that are solid-like but at high magnetic field. Now, one of the challenges is that in space and in naturally occurring complex plasmas, magnetic fields are always present. But space is really big. So even if the magnetic fields are small, you've got a lot of space to magnetize the particles. We don't have that problem. We have a really big problem on Earth because we don't have that much space. And so if you consider, for example, a typical refrigerator magnet, this is our little lab magnet, something like this, then it has a certain magnetic field. You can throw it, you can stack it to your refrigerator. You could go to a typical MRI, and they're maybe about 100 times stronger than that typical refrigerator magnet. We have a laboratory at Auburn in the Leach Science Center that produces a magnetic field that's about 400 times stronger than a typical refrigerator magnet. And it's quite large, as you can see by a standard unit physicist standing next to that particular experiment. So, what happens? When we performed this experiment with the magnetic fields, we discovered something quite remarkable. This experiment's been running for about a year and a half. It's a wonderful new tool that we have available to us. And we discovered something remarkable, that with increasing the magnetic field, we got a new type of complex plasma system that formed a new type of crystalline structure, not by changing the temperature of the system, but by changing the magnetic field in the system. And as you go from low magnetic field on one side to the high magnetic field on the other, the system actually crystallizes. And the beauty of that is that means that if I take those videos, sum up the frames, I can now organize and build structures in the plasma that have a whole variety of shapes. And our question that we want to be able to answer is that, can we in fact build to-order structures in plasmas using our tools with these high magnetic fields? And so, going back to the title, how can we use complex plasmas to represent all four states of matter? It's a remarkable thing. We can now tune these systems. We can now make them behave solid-like, liquid-like, and gas-like. And of course, then, you get just remarkable videos like this, taken by one of my undergraduates, of these particles levitated inside of one of our experiments. This is not work done by myself. This is done with a huge research team. I have my collaborators at Auburn. We have a research team extending across the US and, in fact, across the world with the international dusty plasma community. And this work is supported by a variety of agencies, including the funding for the space station work from the European Space Agency and DLR. And with that, other than some sources, thank you very much.